Okay, so the second half of this is talking about atmospheric pressure. So we'll talk about things like what pressure is defined as. I know I mentioned it a little bit in the last one. Different units that pressure can come in, how to convert units of pressure, and we'll take it from there. Okay, so as I mentioned in the previous video, pressure is caused by the number of collisions happening within the walls of a container, or actually any collisions period with objects in their path. So typically, pressure is equal to the force per unit area. Okay, so this is an important point here. The greater the area, the lower the pressure. Alright, so let's imagine for a second I have two different boxes, right? And I'm going to have the same amount of gas in each box. Okay, so let's say 6 molecules of gas. So you have to imagine if inside these boxes, right, and everything's the same, right? So like same amount, same temperature, same type of gas, like imagine everything else is constant, right? So these particles are going to be bouncing around inside these containers, right? So they're basically going to be all over the place. You have to think which container would have more collisions happening. So let's say we had box A, and then this guy here is box B. So box B is what I'm hoping you responded with, is going to have way more collisions than box A. The reason why is because it's just a smaller space, so the particles are just going to hit something more often than this one with a larger space. So the more volume you have for a gas, the lower the pressure is. So A would have low pressure, whereas B would have high pressure, like comparatively. Right? So the greater the area or volume, right, the lower the pressure would be. So pressure is the force created by the collisions of molecules with the walls of the container. So always go back to thinking, will this have a lot of collisions or a lower amount of collisions? The more collisions, the higher the pressure is. Now, pressure comes in a variety of units. Okay, so just like you can have volume being, in America, right, the empirical system uses ounces and gallons for volume, right, whereas the rest of the world uses liters and milliliters. So pressure is actually one of those strange things that it's actually accepted to have different units of pressure depending on the industry or the way we're describing pressure. So in terms of the unit we're going to be using most often, that's going to be Pascal. So you'll notice here I have here, it's the international pressure unit. Just like liter is an international system for volume, the Pascal is that for pressure. Now, millimeters of mercury and torr are both units that are used within the health industry. So for example, millimeters of mercury is used quite often for measuring blood pressure. So even though it's not the international accepted unit, you do see this quite often. Atmosphere is a unit of pressure that's used primarily in the environmental field. So for example, if we're talking about the atmospheric pressure and we're talking about if it's going to rain outside, right? People who are predicting the weather will use units of atmosphere for their measurements. So you do need to be comfortable of going in between these units. But when we're doing calculations, for the most part, we're going to be doing Pascal. All right, so now we have these things called standardized units. Okay, so we have two sets of conditions. We have something that's called a standard, and we have something that's called a standard ambient. And actually, we've seen standard ambient before, right, when we talk about other things, other factors that are measured at SATP, if you remember that. So there's also something called STP. So what that stands for is standard temperature and standard pressure. So this here is talking about what standard pressure is. So standard pressure, and all of these are measured at sea level, so meaning the lowest point that you can get to on Earth. So not high in the Alps or high on a mountain, but like water level essentially. The average atmospheric pressure, so at the standard pressure, is 101.325 kilopascal. So remember, we're dealing with pascals, so 1 kilopascal is equal to 1,000 pascals. So because pascals we have quite a bit, we usually are dealing with kilopascal rather than pascal. So this measurement is used to define what 1 atmosphere is. Okay, so what that means is, we talked about all those different units of pressure. This is a way of knowing what each of them is equal to. So 1 atmosphere is equal to 101.3 kPa, which is equal to 760 millimeters of mercury, which is equal to 760 torr. So this is going to be kind of like our conversion units. So meaning, let's say we have torr, but we want to convert into kPa. Well, once we know what the relationship is and how much they are equivalent to each other, we can solve for an unknown. And I'm going to show you that later on in the lesson. Okay, so standard temperature. So remember, STP stands for standard temperature and pressure. So we already talked about standard pressure. Standard temperature is 0 degrees Celsius. Okay, so standard temperature is 0 degrees Celsius. So when we say STP, or we could say, the following reaction is occurring at STP. What that means is it's happening at 0 degrees Celsius and at one of these units of pressure, right? You also have this STP written on your pink data sheet. Or your data sheet. It's at the top, and there is a chart at the very top where it says final exam data sheet. It's the first chart right underneath that title, but I will show you later on. But you should be able to find it quite easily. Alright, so then we have another set of standard conditions which we have seen before. SATP, so standard ambient temperature and pressure. So standard ambient temperature is 25 degrees Celsius and standard ambient pressure is 100 kPa. So these are also on that data sheet. Okay, so sometimes you're going to see SATP pressure, instead of saying 100 kPa, what you might see in your textbook or online somewhere if you're looking at this, is 0.1 megapascal. So 0.1 megapascal is the exact same thing as, saying 100 kPa. So it's just like it's like I'm saying, 0.1 liters is 100 milliliters. It means the same thing, it's just a different way of expressing it. I will not use megapascal, okay, but I'm just kind of letting you be aware of it, so in case you come across that somewhere along the way. Alright, so if you see SATP, what does that translate into? 25 degrees Celsius, 100 kPa for our pressure. Alright, so let's talk about now, let's say we did have to convert our pressure into different units, how we can do that. So first of all, the relationship between all the units is right here. I will provide this for you. Okay, so you will never have to memorize how many kPa is equal to how many millimeters of mercury, etc., etc. This I will provide for you on your test, on your exam, anytime that you require it. But you need to know how to use this information in order to convert units. So here's an example. And actually the easiest way to explain how to do this is exactly the same way we've been doing the mole ratio. All right. So let's look at our questions. We have convert 710 millimeters of mercury, into kPa. So X is what we want. We want units of kPa. What we have is units of millimeters of mercury, 710 millimeters of mercury. So on the right side, instead of writing your coefficient, what you're going to do is you're going to write in the values from the unit conversion little chart here. So if the numerator is kPa, you're going to write what the value is of kPa in the numerator on the other side. My denominator is millimeters of mercury, so the denominator on the other side has to be the value of millimeters of mercury. Once you have this set up, you're doing cross multiplication and solving for X. Alright, so the last little bit here, we're talking about what atmospheric pressure is. So hopefully up till now you kind of understand what I mean when I say the pressure inside of a container, right? So looking at the collisions within the walls of the container. The smaller the space that you pack that gas into, the higher the pressure because there's more collisions. But when we're talking about collisions in the air, so when we talk about our atmosphere, technically the container that we are in is our Earth, right? Like our planet. So when we say we're measuring atmospheric pressure, technically what that means is we're looking at the number of collisions happening with the surface of the Earth. The more collisions of air particles on Earth's surface, the higher the pressure is. As you go higher and higher up into the atmosphere, so let's say we're at the top of a mountain, there are less and less collisions happening with the surface of that mountain. Now the reason why that is because there's more space between particles the higher up you go in the atmosphere. And there's a reason for that. Gravity is essentially pulling down air particles. Just like it's holding me and you down onto the Earth, it's also holding down air particles, right? So oxygen, nitrogen, all the things that are in air. So the closer to the Earth's surface it gets, the more it feels that pull down. It's almost like the weight of all the particles above it are pushing down on the surface. So, essentially, the number of collisions that are happening with Earth's surface is what we call atmospheric pressure, right?